So today we are going to wrap up our discussion of N-wells by talking about RC delay. And I think we might get out of here a little bit early. It's Friday. I'm sure none of you guys will be wildly offended. So instead of moving on into our next topic, which if you're following along in the textbook, most of the stuff that we've been talking about here is going to be in chapter 2. The next chapter in the textbook is all about the metal layers. That's not what we're going to talk about next. Instead, we're going to be talking about the polysilicon layers next, because polysilicon layers are the next things that are actually fabricated in the fabrication process. And I want to go with that kind of methodology, which will make the concept of self-aligned gates, which is what's commonly used, make a whole heck of a lot more sense if we talk about the poly layers before we talk about the metal layers. So anyway, RC delay through N-well. So we have observed that an N-well region has a resistance and any actually, I don't even put that, and a capacitance. I was going to say any biased, but there's going to be an unbiased junction capacitance that we will be dealing with too. So really, any N-well region has some finite resistance and a capacitance, resulting in the formation of an RC network. So, kind of symbolic representation of what's going on here. Here we have our substrate. I have my N-well region, which I'm drawing in purple. And let's say, for the sake of argument, that I'm applying some input voltage on the left-hand side of my N-well, and I'm taking some output voltage on the right-hand side of my N-well. We are not in any way, shape, or form discussing yet how we actually get signals onto or off of our chips or anything like that. I actually have a situation that looks something like this. So I have my resistance, and then also some capacitance to take into account, and the bottom plate of my capacitors are all tied together. They are at ground potential, since my substrate is usually ground. So I have my N-well resistance being represented by each of these resistors, and then I have my depletion capacitance being represented by all of those capacitors. Okay. Another way to look at this guy And this is directly from your textbook. I'm actually not a fan of this representation because it's a little confusing. Is this guy. So what I find confusing about this representation is that that circuit element that is a resistor but also a capacitor plate doesn't exist. A more reasonable model would be this guy. I'll call this R, call this C. Here's my input voltage. Here's my output voltage. Now, really, I'm going to put an R prime here and a C prime here because we're about to do some transmission line theory work, okay? So I'm modeling this guy as an RC network where this is actually, instead of a lumped parameter model like we're used to doing with regular circuit analysis, we are going to develop a distributed parameter model, which would be representative of a section of transmission line. So really all that means is that we're going to have resistance per unit something and capacitance per unit something. And because we're dealing with a planar system, those are going to be resistance per unit square and capacitance per unit square, or the sheet resistance we've been dealing with, and our unbiased junction capacitance CJ naught per unit area. Okay, so nothing particularly fancy there. So we can make a homogeneous ladder network. Well, actually, we'll do that in just a minute. Okay. For a simple RC circuit, so let's say that we have something like this. I have a step function at my input, Vn. I have some resistor R. I have some capacitor C. And I want to know what my output voltage is. Graphically, what should that input-output relationship look like? Anybody remember any of this stuff from literally circuits 1? So if I plotted my input signal, I just have a simple unit step function, right? So this blue curve is going to be Vn, and I'm going to call the height of this guy V pulse. Unit step, right? It is 0 volts until it gets switched on, and then the input voltage jumps up to its maximum value, and then it stays there effectively until we turn it off. So what happens if I apply a unit step function to an RC network? What is the transient response of any RC or RL network going to look like? An exponential function, right? So we're going to see, this will be my output signal. That is not blue, or that's not red, I mean. It's going to take some time. It's going to hit that same value and then stay there, right? So we observe some delay in our signal. All right. So mathematically, we could relate this as V out as a function of time is going to be equal to V pulse, the maximum value of the voltage, multiplied by a factor of 1 minus e to the negative t divided by RC, where RC is the time constant for this simple RC network, right? So the reason why it's not just the simple exponentials, because we're looking at a charge cycle, not a discharge cycle. So we need it to start at 0 and then increase, which is what's being forced to happen by this mathematical expression right here. And it settles to a value of V pulse as time continues. All right. So we're going to define a couple of things here. All right. The first thing that we're going to define is the delay time. So the delay time will be the time it takes the output signal to reach 50% of the input signal level. So if we know that we want our output to be half the size of the input signal level, we could say that 0.5 V pulse must equal V pulse times 1 minus e to the negative t over RC. We have a common factor of V pulse on both sides that we could get rid of. We could take the natural log of both sides, and what we wind up finding is that our delay time, d, will be negative RC times the natural log of 1/2, or approximately 0.7 times R times C. You might see it in some textbooks as 0.69. Those are only two values I've seen. They're close enough. It doesn't really matter which one you use here, okay? So roughly 70% of a time constant is how long it takes our time to change from its initial value to half, right? Where a time constant was defined as e to the -1, or the time it takes to reach 37.9% of its original value. So it's the same basic concept. We're just looking at it from a slightly different perspective. We are also going to define the rise time. And for those of you in the lab, and I mean the ELEN 439 lab, the rise time definition that we're using here is the exact same rise time definition that is used to determine the slew rate of an op amp. So if any of you guys are researching that, if you haven't been screwing around, this should look familiar. So the rise time will be the time it takes output signal to go from 10% of the input signal level to 90% of the input signal level. So mathematically, to determine my, rise time, I don't know why I wrote it down as TD in my notes. That doesn't make a lick of sense. So my rise time, I'm going to look at the 10% value first. So that would be 0.1. B pulse is equal to B pulse times 1 minus e to the minus tau over RC. And 10% then is approximate, or is a negative RC natural log 0.9. For my 90% level, 0.9 V pulse will be equal to V pulse times 1 minus E over RC, giving me a T 90%, that is negative RC natural log 0.1. And finally, then TR, my rise time, is simply T 90% minus T 10%, which is negative RC natural log 0.1 minus natural log 0.9, approximately 2.2 RC. So that's how we would define everything for a simple RC network. But depending on the size of our N well, this might not be a good model. Okay, and we'll talk about what I mean with regards to those size constraints momentarily. So a more accurate model from a circuit perspective would be a distributed ladder network. And it'll be a homogeneous network, which means that all of the elements will have the exact same value. So it's consistent all the way through. So for our homogeneous ladder network, that would look something like this, where we have and I'm going to call this guy right here node A. And we have another resistor that is R squared, another capacitor that is C squared. I'm going to call this guy node B. And this unit cell, if you will, that is just the simple RC network repeated over and over again, but we're looking at it from a distributed standpoint, forms our ladder network. Let's call that node C. And then finally, over here on the far right-hand side, we have a node N, over which our output voltage is measured. So delay characteristics of this guy are going to be a little bit different. Did you guys cover any transmission line theory in your 411 class with Dr. Cox? Okay. So why does it take time for signals to propagate through a transmission line? Because that's exactly what this is. Anybody got any thoughts? Why does it take time for the signal to propagate through the single RC network? Because it takes time to charge the capacitor, right? So here we have a bunch of capacitors. They're not in parallel, but so we can think about it. If we apply some input signal on the left-hand side, right? Current is going to flow through that resistor RD, or excuse me, not RD, R square, but the rate at which current flows through that resistor RD depends on R square. I'm going to have to redraw that to not look like a D, or I'm going to keep saying it. It depends on the voltage level present across that first capacitor, C squared, right? Once that capacitor finally charges, then the signal will start propagating further to the right, and that cycle repeats itself over and over and over again. So at node A, the delay time is simply 0.7 r squared c squared, right? Because we just have one section of the ladder network that we're worried about. When we get to node B, it would be 0.7 times r squared c squared plus twice r squared c squared, right? So we have to charge all the way up to the second node, and then we have to recharge the first node as well. And then for node C, it's going to look like TDC is 0.7 r squared c squared plus twice r square c square plus 3 times r square c square. Hopefully you all can see the pattern forming here. So the delay to node N will look like, and this is going to be the overall delay time for this distributed network, 0.7 r square c square times 1 plus 2 plus 3 plus all the way out to n, or 0.7 r square c square times the summation of from I, right pen, is equal to 1 to n of I. Well, we can approximate this. What would this be, an arithmetic series because we're adding all the things together? As 0.7 r squared c squared n times n plus 1, or sorry, actually, I screwed that up. I forgot to factor 1/2 in here. When we do that substitution, it'll be 1/2 n times n plus 1, which looks like 0.35 r squared c squared n times n plus 1. All right, so this is where we start talking about the size of the wells making a very, very significant difference here, all right, between our simple model and our distributed network model. So let's say that we have a small system. So there are only a few squares, right? We would see that the difference between this model and the lump element model would be vastly different. Okay, so let me explain what I mean here by the lump element model, because it should be pretty quick. I'm going to put some arrows out here. So this is our distributed model. We could say that this guy that I have right here, when n is large enough, looks like 0.35 r squared c squared just times n squared, right? If n and n plus 1 are large enough, then n times n plus 1 is going to be pretty dang close to n squared. Well, I can distribute that and say that I have 0.35 r squared times n times c squared times n, which is the same thing as 0.35 R total times C total. So there's a difference of about 50% between the distributed parameter model and the lump parameter model when we consider the lump parameters to just be the number of squares of resistance we have times the resistance of a square, and the number of squares of capacitance we have times the capacitance of a square. So it's a really, really big deal as far as accuracy to use a distributed parameter model versus a lump parameter model to understand what's going on here, okay? We could follow a very similar derivation and get a distributed rise time for this same network, TR, of 1.1 R square C square times N plus 1, where again, we wind up using the same arithmetic series and all that kind of stuff to explain everything. So that's why we effectively just cut the result in half and we have what we have. So this is the delay that is caused by effectively the transmission line network that is formed, okay? But there's a secondary delay that we need to keep in mind as well. For an N-well resistor, it's practically never going to matter. But once we start talking about propagating signals down metal runs and stuff like that, this is a really, really big deal, okay? So I want to define the intrinsic delay. So the intrinsic delay is the time it takes to propagate, I might be misspelling propagate. I can never remember if it's an A or an O in the middle. Time it takes to propagate a signal through a particular medium, right? So what I mean by this is it takes a different amount of time to propagate a signal through a copper wire as it does through air, as it does through material with a high permeability, as it does through a material with a high permittivity, right? So our intrinsic delay time, TID, is simply the square root of mu r epsilon r, the relative permeability multiplied by the relative permittivity of our material of interest, divided by the speed of light c, multiplied by the distance we're trying to propagate our signal. Okay, so in silicon, for, I would even say a long run, so something on the order of a couple of hundred microns to maybe a few millimeters, we expect this guy to be less than 100 picoseconds, right? Typically speaking, it's going to be smaller than that, but less than 100 picos. Actually, that's the wrong, but greater than, I meant less than, sorry. So less than 100 picoseconds, or let's see, so that would be 10 times 10 to the, no, 10 to the minus 10 seconds roughly, or smaller. So let's calculate, let's work an example here real quick, and this will be the last thing we do for the day, so that I can finish up your homework assignment. We want to estimate the delay time through 250 kiloohm and well resistor with a length of 10 lambda, excuse me, sure, length of 10 lambda and a width of 500 lambda. Assume capacitance of a 10 lambda by 10 lambda square of n well substrate is 5 femtofarad and okay, that's all the information we need, sorry. So one thing that I can say about this problem, it's not explicitly stated, but we are going to be neglecting sidewall capacitance in this case. And it's because the physical dimensions of our resistor are so much so it's really, really long, right? So we should expect that the area, the bottom area is going to be contribute more than the perimeter. So let me copy this problem over actually so that we can do it all on the same page. See? How would we go about answering a problem like this? Let's start with our delay time equation. 0.35 r square c square n times n plus 1. What do we know? C square. That's it, right? As far as these parameters go. So we need to figure out what n is, and we need to figure out what r squared is. How do you think we're going to do that? Okay, so we're trying to figure out what r squared is. What we know of our resistor are 10 lambda by 500 lambda, and our total resistance is 250 kiloohms. So I would argue that that amount of information will actually make it pretty easier for us to calculate what n is as well, right? And then we could figure out what r square is by dividing our total resistance by n. So what's n got to be? 50, right? It's the ratio of the length divided by the width, or width divided by length, right? So there are going to be 50 10 by 10 lambda, or 10 lambda by 10 lambda squares comprising this resistor. Which means r square ostensibly would be 250 kiloohm divided by n of 50 is 5 kiloohms per square. Seem reasonable? All right, so from this, our delay time, TD, is equal to 0.35 times 5 kiloohms times 5 femtofarads times 50 times 51, which I get to be, I believe, 22.3125 nanoseconds. Now, just for the heck of it, let's figure out what the intrinsic delay time would be for lambda is equal to 500 microns. Epsilon R for silicon is 11.7 unitless quantity. Mu R for silicon is real close to 1. Speed of light in a vacuum is 3 times 10 to the 8 meters per second. So our intrinsic delay time, TID, is going to be the square root of 11.7 divided by 3 times 10 to the 8 meters per second. And then we're going to have, let's see, so how long is this guy going to be? How long is our, so 500 lambda. Or 500 times 500 times 10 to the minus 6 meters. So meters cancels meters, and we get, so our answer should be in seconds. Who's got a calculator? I think I forgot mine. 2.85 nanoseconds, all right? So 2.85 nanoseconds. So let's think about, so that's a bit larger by roughly an order of magnitude than I said we should expect our intrinsic time to be. But think about that length, right? So we have 500 units of half a millimeter. So 250 millimeters. We're trying to send this signal through a 10-inch distance on a chip. And the intrinsic delay time would be less than 3 nanoseconds. So even in this case, where we're trying to send it over a hugely long distance, we still observe that the RC delay time is going to be the thing that actually governs how long it takes the signal to propagate down the transmission line. Okay. When we get to metal systems, that won't always be the case. That's because the sheet resistance of metal, so for this 5,000 kiloohm, or excuse me, 5 kiloohm sheet resistance for an N well is really about 5 times as large as what you would see. In a C5 process, it's typically somewhere around 800 ohms per square, plus or minus 20%. The sheet resistance of your metal layers that we're going to be talking about probably later on next week are usually on the order of less than an ohm per square. So you can see why that RC delay is going to go way, way, way down when the R value goes way, way, way down, and the ability of the material to propagate your signal becomes much more important. All right, anybody got any questions or anything like that for me? We have wrapped up in a week's time, chapter 2 of the textbook. All right, so if you don't have any questions for me, I'm going to post your homework today before 5 p.m. when I leave. Probably, hopefully get it up before my next class at 2:30. It'll be due next Friday at 5 p.m. as all the homeworks in this class will be due Fridays at 5 p.m. This homework assignment will involve some mathematical calculations and all that kind of good stuff, as well as some use of electric to lay out some N-well resistors and that kind of thing, just so that you're getting experience playing around with it. Yes, I will post the homework on Moodle. Also, please wear your mask to class next time, Desmond. I didn't notice you weren't wearing it until now.